Hello all, I welcome you all to the second part of lecture 20. In the previous lecture, we saw how you can understand the surface charge density uh, versus the surface potential is, and we saw various regimes. When you have a surface potential lesser than 0, you have what is called as the accumulation, and in this regime, so let us take a look at what physically happens. And I want to actually go a little bit slower here because it really helps us to understand what exactly happens, right? So I want to do in two places. One is the physical space. So let's take a metal semiconductor insulator here, right? And if I apply, so this is a PMOS. If I apply a negative potential leading to negative surface potentials, it's easy to see that I will accumulate holes from the majority bulk, right, to the interface, and the electrons will be repelled out. After a certain point, your holes will form a sheet of charge carriers here, screening out all the potentials, and hence the electrons will not be affected, right? So this is the accumulation region. And why does the charge increases with the potential? Basically, you have a tremendous number of hole concentration in the material, and hence you have a very high capacitance in this particular point. So whatever potential that you apply, it will be compensated with equal hole charges from the semiconductor side, right? So and then hence you have this linear increase in or exponential increase in the charge density with the applied potential. Now let's go back. Let's go and look at the situation in the wait. Before we go there, let us take a look at the band diagram, right? So this is a p-type semiconductor. I have a Fermi level of the metal here, right? So it's something like this, and all of them are bent like this. Let's take the Fermi level here, and the intrinsic is like this, right? The more positive potential that I apply, the more the valence bands will bend up, and hence it will start, the valence bands will, the band will start crossing the Fermi level at this particular point, and hence you can continually accumulate charges to how much ever potential that you want, right? So you will have a huge density of carriers here, giving you this particular behavior. Now let us look at what happens when you apply a positive potential to a PMOS MIS structure, right? So I take a semiconductor here, again apply a positive potential, right? If I apply a positive potential, of course the holes are repelled. If I repel the holes, I will start to have negative charges here, but now not from mobile charges but from immobile donor or immobile acceptor ions here. So what happens to the band structure under such situations? I have a metal work function like this, right? And because of the fact that the holes are removed, the bands have to bend in this particular fashion, right? And I have the Fermi level here. Now you will start depleting the channel because of the fact that it's a p-type semiconductor. Your conduction band is still not very close, so you will have to actually move. So let me, right? And this is psi b, right? And this is psi s, remember, right? So this is ei equal to 0, right? And when you apply a potential, this ei starts to bend, and the extent of its bend is psi s, and extent of its the difference in the energy levels of the Fermi level and the ei at infinity is psi b, correct? So if I start applying positive surface potential such that I increase psi b, psi s, and make it closer and closer to psi b, you can see that I will start depleting more and more, right? And hence you'll have this particular region dominated by depletion, right? And the more I move, now I start the conduction band to become dangerously close to the Fermi level, and then I will start to have some weak inversion. In weak inversion regime, I actually start to populate holes in a p-type semiconductor, and hence it is called as an inversion, right? So basically you are populating more and more minority carriers in a p-type semiconductor, minority electrons in a p-type semiconductor, right? Now if I increase the surface potential further such that it increases more than twice or close to twice the separation of the majority carriers, right? So now I have equal number of minority carriers in comparison to majority carriers, and hence you have a region what is called as strong inversion, right? So now let us take a look at the situation under strong inversion. I have a metal work function. This is an insulator, right? And I have a band bending. I have a Fermi level here, and I have an intrinsic level, something like this, and this is psi b, and this is psi s. So if I draw the charge profile in this particular diagram, it's easy to see that, let's say I will have a very thin sheet of charges in the metal, right? So this is QM, and I will have a very strong density of mobile charges at the interface and some depletion, and let's say the depletion width is WD, and the area under the depletion width will turn out to be minus Q Na into WD. Na is accepted doping density, right? And this is, let's say, minus Qn. And it's easy to see that because of charge neutrality, Qm should be equal to minus of Qn plus Na Qna WD, and which I write together as minus Qs. So this is the total charge in the semiconductor side, right? And if I draw the electric field in this, electric field is just an integration of this charge profile. So the electric field will turn out to be something like this, right? And at this junction there will be a sharp drop, and here I will have a very slow drop. This is the electric field, and the potential profile is again an integration of this. So the potential will be parabolic here, much stronger parabolic, and it will have a linear increase in this region and will remain flat after this, right? So basically this particular value will be the V applied, right? And it's easy to see that the one that is linear is the actual potential on the insulator, and you have this potential on the semiconductor, right? So from the Poisson's equation derivation that we currently saw, the total applied voltage will be V on the insulator plus psi s, that is the surface potential, right? So this is psi s. as we currently saw, right? And you can easily see that the voltage at the, or the potential at the interface, is basically epsilon I into d, which will turn out to be, sorry, ei is the electric field at the intensity, so electric field at the insulator. So this is ei, which will turn out to be qs by epsilon I into d, which is qs by ci, where ci is a insulator capacitance, right? So because of the fact that you have an insulator here, you have what is called as a capacitance, right? You'll have a capacitance for this, geometric capacitance for this insulator. So ci is the insulator capacitance, and you can see that we previously saw that the semiconductor will have what is called as a depletion capacitance, which is coming from the depletion width at the metal semiconductor interface, and then now you have an insulator capacitance. And because the total voltage applied follows this particular rule, you can see that the total capacitance is a capacitance of two capacitance in series, and hence total capacitance will turn out to be ci cd by ci plus cd. Ci is the insulator capacitance and cd is a depletion capacitance, and ci is just epsilon I by d. These are all area normalized capacitances, right? So now that we have these things, now let us see what happens to the total capacitance for various applied voltages and at various frequencies, right? So now, because the total capacitance depends upon the depletion width and the insulator capacitance, it has a dependence. Total capacitance depends on, one, applied bias. Why? Because it changes the depletion capacitance. Two, it also has to do with the frequency of measurement. We will see this particular aspect very soon as to why it depends upon the frequency of measurement. Regarding to the applied bias, it's easy to see that if I increase the positive surface potential, if I increase the applied V, it will obviously increase the surface potential S, and if it increases surface potential S, you can see that it changes the depletion width, right? So now let us go as we did before for the charges. Let's see what happens at various applied potentials. I'm going to plot C total by Ci. Ci is the insulator capacitance across various applied bias potentials. And this is at V equal to 0, right? Now, so now let us calculate the total capacitance. To do that, we have to know what is the depletion capacitance at various bias potentials. So at V lesser than 0, let's see what is the, and let's see what is the depletion capacitance CD, which is dqs by d psi s, and dqs we know is d by d psi s. Qs is plus or minus root 2 epsilon s kt by qld square root of e power minus beta psi p minus 1 plus e power now if I do the differential, what I will get is epsilon s by root 2 ld 1 minus e power minus beta psi s plus np naught by pn naught e power beta psi s minus 1 by f beta psi s by p naught by p naught, right? So if psi s is negative, you can see that CD is a very large value, right? Because it goes exponentially with psi s with a positive value, right? So at very large depletion capacitance, the total effective capacitance is actually dominated by the smaller capacitance value, right? Because it is given by this. So the one which is smaller in comparison will actually dominate the effective capacitance, and hence in the accumulation region the total capacitance that you will get is the geometric capacitance, and hence you will have something close to 1 till the point you have V greater than 0, till the point you have a positive, till the point that you have a negative surface potential, right? Now when you go to a positive surface potential, let us take a situation, second situation, when psi s is 0, V equal to 0, right? Under this situation you can see that the f function, which is beta psi s np naught by pp naught, will tend to 0. But then to actually resolve this you have to use the L'Hopital rule, and then if you substitute the exponent in the Taylor series, you can see that CD will drop to what is called as epsilon s by LD, which is called as the flat band capacitance. So at psi equal to 0, the capacitance is not the geometric capacitance but what is called as a flat band capacitance, and the total capacitance will turn out to be epsilon I epsilon s divided by epsilon s d plus epsilon I LD, right? Now let's go back to the third situation when psi s is positive greater than 0 and psi s is lesser than psi b. Under this situation we know that f goes as root of psi s, and we know that the total charge in the depletion width is q wd and na, and with this you can substitute with our previous equations that v total applied voltage is vi plus psi s, and vi is qsd by epsilon n, and if you substitute all of them to this together, you will get what is vd to be root of epsilon s square by c insulator square plus 2 epsilon s v being the applied potential by qnd minus epsilon s by cox, right? So basically what happens is under these situations you have the depletion capacitance CD much smaller than the geometric capacitance, right? And hence the total capacitance will now drop and will reach a value V min, which is between psi b and 2 psi b. And it is at this point when you have 2 psi b, obviously you will have a strong inversion, and hence your capacitance will again raise up. Now whether this feature will happen or not depends upon the frequency of operation. Why? Let's consider that again, right? So okay, so now if we increase V such that psi s is equal to or greater than 2 psi b, then you reach what is called as strong inversion. But this is not always true, right? So it depends upon the frequency of operation. Why? Because the strong inversion depends upon the ability to generate minority carriers and then bring them to the interface, right? If the frequency of operation, that is CD, is actually dqs by d psi s, so at a particular frequency omega, if the frequency of operation is much larger than the rate at which the minority carriers are generated, what you have is, if I plot the metal carrier density and the depletion width, right? So at low frequencies, any increase in potential will generate carriers in the metal side here, and will generate carriers in the at the interface by the mobile charges, right? However, if you increase the frequency, instead of actually forming charges at the interface by mobile carriers, you actually increase the depletion width here. So basically, because of the fact that you are not able to generate the minority carriers at the rate at which the frequency, at the rate at which the capacitance is measured, right? So what happens is, instead of at low frequencies, you will have the capacitance which will again rise up. So this is what is called a strong inversion. Right? At low frequencies, you actually have the strong inversion. However, at high frequencies, the capacitance do not increase because of the fact that the minority carriers do not respond to the frequency of operation, and hence the depletion width is what is will respond to the AC bias that you have applied to measure the capacitance. Right? So any change in metal charge density will reflect in charge density in the depletion width, and hence the capacitance CD is dominated by the depletion capacitance, giving you a flat line here. However, you have what is also called as deep depletion. If what happens is, if you increase the if the voltage bias, this bias potential VB is also swept at very high frequencies, then what happens is uh, your total capacitance drops even below the high frequency limit, giving you what is called as deep depletion. And hence here, so you will not have the surface charge densities respond, or you will not have even surface charge densities, because your actual potential bias has moved so fast. You will have a depletion width which is much enhanced, and then it is only this which will move with respect to the metallic charge densities. This is rho of x, and this is WD, and you do not have any mobile charge densities at the interface. This is the situation when you have deep depletion, right? So at this stage we will stop, and the next time we meet, let us talk about non-idealities or interface traps in metal insulator semiconductor junctions.